Welcome back to AK Virtual Maths, everyone. Today, your favorite professor is here to completely demystify the microscopic world of giant covalent structures. Let's just dive right into this Chapter 2.6 material, shall we? Take a look at this beautifully sparkling diamond on the left and, well, this completely ordinary graphite pencil on the right. Now, would you believe me if I told you they're made of the exact same element? Seriously, no joke, they are both 100% pure carbon. Here is our lesson plan for today's explainer, perfectly crafted for both our core and extended syllabus students. We'll welcome you to Giant Structures, explore diamond and graphite, pause for a quick concept check, look at silica, and wrap up with a summary. Section 1. Welcome to Giant Structures, defining the basics. Let's kick things off by locking down a couple of key chemical terms you're absolutely going to need for your exams.
Take a look at these two objects, a sparkling diamond and the lead inside a standard wooden pencil. They look and feel entirely different from each other, yet both are made entirely out of the exact same ingredient, carbon atoms. Their unique traits come down to how those carbon atoms are connected. Think of the atoms like identical plastic building blocks. You can snap the exact same pieces together to build a strong, solid wall, or you can stack them lightly to make a tower that easily tips over. In chemistry, we have a specific name for this. We call them allotropes. Allotropes are different physical forms of the exact same element.
An allotrope is simply a different structural form of the exact same element. So, since diamond and graphite are both completely made of carbon, but their atoms are just arranged differently, we call them allotropes of carbon. It's kind of like having the exact same Lego building blocks, but using them to build a completely different house. Next up is macromolecule, which we also call a giant covalent structure. This is a massive number of atoms held together in a continuous lattice by really strong covalent bonds. Unlike a tiny, puddle of water or a single floating molecule of carbon dioxide, these allotropes form massive, continuous 3D networks locked firmly together. Section 2. Diamond, the 3D jungle gym. Let's zoom in on our first macromolecule diamond to see exactly why it is the hardest natural substance known to humanity.
To understand how these two carbon objects get their unique traits in the real world, we have to shrink down and look closely at their invisible, microscopic blueprints. Let's start by zooming deep inside the structure of a diamond. Here, every single carbon atom reaches out and locks tightly onto exactly 4 neighboring carbon atoms. We call these strong links covalent bonds. A covalent bond forms when 2 atoms share a pair of their outer electrons, anchoring them firmly together. Because each central atom makes 4 of these connections, those bonds naturally push away from each other into a 3-dimensional pyramid shape. We call this a tetrahedral structure. This creates a repeating 3-dimensional web. Every single atom is firmly trapped in place by 4 unbreakable bonds. That microscopic, rigid framework is the reason a diamond is the hardest natural substance on Earth. Engineers relied directly on this specific atomic property. They embed diamonds into the tips of heavy industrial tools to cut easily through solid rock and metal. But there is a trade-off to this strength. Because every outer electron is locked up making those 4 bonds, there are 0 loose electrons floating around. Without any free electrons to carry a charge, a diamond completely blocks the flow of electricity. To melt a diamond, you need a staggering amount of heat, over 3,500 degrees Celsius. Because every atom is locked into one continuous giant structure, you have to provide enough energy to physically snap billions of those strong covalent bonds all at once.
Okay, I want you to imagine a microscopic, perfectly welded 3D jungle gym. In a diamond, every single carbon atom forms 4 incredibly strong covalent bonds with its neighbors. This forms what we call a tetrahedral shape. It is a super rigid, repeating pattern that absolutely refuses to budge. Because of this rigidly locked structure, diamond has a massive melting point of around 3,550 degrees Celsius. It's incredibly hard, and crucially, it does not conduct electricity. Why? Well, every single outer electron is locked tightly in a covalent bond. There are literally 0 free electrons left over to carry a charge. And what's really cool is how this microscopic rigidity translates directly to macroscopic real-world uses. I mean, we don't just use diamonds for sparkly rings. We actually use them to coat the edges of heavy-duty drill bits and cutting tools. When you need to slice through solid rock or glass, you call in the hardest substance on Earth. Section 3. Graphites, slippery shapeshifters. Now, let's contrast that solid, unyielding jungle gem with our other carbon allotrope, graphite.
Now, let's step out of the diamond and shrink down into the dark core of our pencil. This is graphite. The blueprint here changes completely. Instead of 4, each carbon atom only holds hands with 3 neighbors. This arrangement creates flat rings made of 6 atoms. These rings link together to form wide, flat sheets. The sheets stack directly on top of one another, but the attraction between the layers is incredibly weak. Think of a stack of loose printer paper. If you push the stack from the side, the pages slip and slide right off each other. That sliding action explains why graphite feels so soft to the touch, and why mechanics often use graphite powder as a dry lubricant to loosen up stiff engine parts and locks. But remember the basic rule of carbon. Every carbon atom naturally has 4 outer electrons. If graphite only uses 3 of them to connect to its neighbors, what happens to that 4th unused electron? That leftover particle detaches from the atom. It becomes a delocalized electron. These loose electrons are completely free to zip like a river across the flat sheets, carrying an electrical charge with them. Because of this internal river of moving electrons, graphite is highly conductive. Manufacturers use this property to build electrodes and the small contact brushes inside electrical generators. By using 3 bonds instead of 4, these identical atoms produce either the hardest insulator on Earth or a soft, slippery electrical conductor.
In graphite, the atomic architecture is completely different. Each carbon atom only bonds to 3 other carbons, which creates these flat, hexagonal sheets. Think of it like stacking a deck of extremely slippery playing cards on top of each other. The bonds within the sheets are strong, but the forces between the sheets, super weak. Because the forces between these sheets are so weak, the layers just slide off each other with ease. This makes graphite really soft and slippery. It's a perfect solid lubricant for engines, and it's exactly why it leaves a dark mark on paper when you use a pencil. You're literally sliding microscopic sheets of carbon right onto the page. But wait a second, carbon has 4 outer electrons to share, right? If it only uses 3 for bonding in graphite, where does the 4th one go? Well, that 4th electron becomes delocalized. It's completely free to move between the layers. And because it can move, graphite can conduct electricity beautifully. This makes it perfect for connecting brushes and electric motors and acting as electrodes. Section 4. Quick concept check pause. All right, students, it's time to test your brain power. But first, I need to bust a massive student misconception. Giant covalent lattices contain 0 ions, absolutely none. Please do not get this confused with ionic lattices like salt. Also, melting these macromolecules requires breaking actual, strong covalent bonds, not just weak intermolecular forces. That's exactly why their melting points are so ridiculously high. Okay, here's your question. Why does diamond act as an electrical insulator while graphite acts as a conductor? I want you to physically pause the explainer right now. Grab a pen, write down your answer, and hit play when you're ready. Seriously, no cheating. Welcome back. So, did you get it right? The crucial point is that diamond has all 4 of its outer electrons firmly locked inside rigid covalent bonds. Graphite, however, only bonds 3 times per atom, leaving 1 free mobile electron to carry that electrical charge. If you got that right, brilliant job.
Let's do a quick check. If you were an engineer who needed a material to cut through solid rock, which structure would you choose? You choose the rigid 4-bond structure of diamond.
Section 5. Silica, diamond's sandy twin. For my extended syllabus students, listen closely, because we're expanding our focus to a compound that acts remarkably like diamond, silicon-4 oxide, or simply silica.
Now, let's leave the lab and step out onto a sandy beach. We are looking at an entirely different material here. The sand under our feet is mostly made of a mineral called quartz. Its chemical name is silicon dioxide, or silica. Let's zoom in to a single grain of sand. Here, we don't have carbon. Instead, we have a combination of 2 new elements, silicon and oxygen. Watch how they arrange themselves. Every single silicon atom forms a strong bond with 4 oxygen atoms, and every oxygen atom bonds back to 2 silicons. Just like the diamond, this creates a continuous three-dimensional web. Chemists call this a giant covalent structure. Because this tetrahedral layout mirrors the diamond's blueprint, silica acts the exact same way. It is incredibly hard, it melts at a massive temperature, and it stops electricity in its tracks.
Even though silica is made of silicon and oxygen, literally the stuff found in common beach sand and quartz, it forms the exact same rigid, tetrahedral macromolecular structure as diamond. Just look at this side-by-side comparison. Structurally, they are absolute twins. In silica, which has the chemical formula SiO₂, each silicon atom bonds to 4 oxygen atoms, and each oxygen bonds to 2 silicons. Because it forms this massive 3D continuous network, silica shares diamond's incredible hardness and its very high melting point. And just like diamond, it has absolutely no free electrons, so it acts completely as an insulator. Section 6. Summary and Final Doubts. Wrapping up Chapter 2.6. Let's bring all this amazing atomic architecture together into one ultimate revision cheat sheet.
Let's put our 2 carbon forms side by side in this table. On the left, diamond has 4 strong bonds locking into a rigid shape, making it hard and non-conductive. On the right, graphite uses only 3 bonds, creating flat, sliding sheets with loose electrons, making it soft and conductive. And why does beach sand behave so much like a diamond, even though it's made of completely different elements? Because they both share that identical 3-dimensional web of strong bonds. The next time you drag a pencil across a piece of paper, think about what is actually happening. You are quite literally sliding millions of atomic sheets off a giant structure. The invisible rules of chemistry are constantly at work, defining the behavior of everything we touch.
I highly recommend you grab a screenshot of this summary table right now. It brilliantly illustrates how the microscopic bonding of diamond and graphite directly dictates their macroscopic real-world properties and subsequently their uses in our everyday lives. Isn't it fascinating? The beauty of chemistry is that the exact same atomic building blocks, just simple carbon atoms, can create both the hardest drill bit capable of cutting through solid rock and the softest pencil lead you use to sketch. Merely changing the structural arrangement of those atoms completely transforms a material's destiny. Thank you so much for joining me today on AK Virtual Maths. I really hope this explainer made giant covalent structures crystal clear. Please like this explainer, subscribe to the channel, share it with your classmates, and definitely drop any doubts you have in the comments below. I read them all. And before you go, think about this. If carbon can be both a soft pencil and a hardened drill bit, what other everyday elements are hiding completely different superpowers? Keep learning, and I'll see you next time.